In this EzEd video lecture, we will learn about optical devices, wherein we will study about light-emitting diodes, photodiodes and their construction, working and applications. We will start with light-emitting diodes, abbreviated as LEDs. In our day-to-day life, we come across many applications of LEDs, such as street signals, LED torches, etc. We have already studied a PN junction diode. Light-emitting diodes are derived from PN junction diodes only. These diodes, when operated in forward bias mode, emit light in all the directions. Thus, the symbol of LED is as shown with two arrows depicting emission of light. Let's see the construction of LEDs now. LEDs also have a PN junction structure with two terminals such as anode and cathode, same as a normal PN junction diode. It is constructed by developing three semiconductor layers on the substrate layer as shown. Out of the three semiconductor layers, one is a p-type layer having holes as majority charge carriers. The other layer is a n-type layer having electrons as majority charge carriers. And in between these two layers lies a third layer known as the active region. This active region emits light when electrons and holes recombine in this region. We will see the working very shortly. As the active region emits light in all the directions, basic layered structure shown above is kept in a tiny cup structure as indicated by the diagram. To identify the anode and the cathode terminals of a LED, special arrangement is made in the construction itself. If seen carefully inside the cup, we observe a cut between two metal strips. The small metal strip acts as an anode terminal and the big metal strip acts as a cathode. This is how a practical LED looks like.
Hey, it's time to concentrate now.
Before moving towards the working of LEDs, we will learn about the valence band and the conduction band. In normal conditions, when electrons revolve around the nucleus in circular orbits, they have very low energy and are bonded to the nucleus only. These electrons reside in the lowest energy band known as the valence band. When in the valence band, electrons neither form any bond with other atoms nor can they carry the current. To become free and carry the current, these electrons come out of a valence band by acquiring the energy and reside in the higher energy band known as the conduction band. Thus only those electrons which are in the conduction band carry the current. To summarize, we can say that the valence band is a band with lower energy level and conduction band is a band with higher energy level. Let's study the working of LEDs. When forward biased electrons from n-type semiconductor material and holes from p-type semiconductor materials cross the potential barrier region and recombine in the active region, these electrons are in the conduction band and holes are in the valence band. As the energies of the conduction band and valence band are different, when electron-hole recombination takes place, the energy equal to the difference between two energies is radiated in the form of light. This difference is known as the band gap or forbidden gap energy, and the effect is called as electroluminescence. This forms the working principle of LEDs. Normally, LEDs with red, green, yellow, blue, orange colors are available. For LEDs, silicon and germanium is not used as their forbidden gaps do not allow light emission in the visible spectrum. Wavelength is too low. Thus LEDs are made up of gallium arsenide and gallium phosphide, etc. Now let's learn the biasing of this LED. LED is biased in the same way as PN junction diodes are biased. Anode is connected to positive of the supply and cathode is connected to negative of the supply. Resistor RS is always connected in series with the LED to limit the current flowing through it and to protect it from damage due to excess current. The voltage drop across conducting LED is in the range of 1.2 volts to 3.2 volts, depending on the material used. LEDs have extremely low reverse breakdown voltage of the order of 3 to 10 volts, so they should not be subjected to high reverse voltages. Let's see the advantages of LEDs now. Different advantages of LEDs are small size and lightweight, available in different spectral colors, have longer life as compared to lamps, can be easily interfaced with any other electronic circuits. Operating speed is high, takes only 1 microsecond to turn on or off. LEDs also have some disadvantages like need larger power for their operation. Luminous efficiency of LED is low. LEDs get easily damaged due to overcurrent. Let's see some practical applications of LEDs. LEDs are widely used in displays of various electronic circuits. Street signals, railway signals implement LEDs of basic 3 colors. LED TVs are available in the market. Very wide application of LEDs is in 7-segment displays. Moving forward, let's learn about the photodiode now. In LEDs, the recombination of electron-hole pair results in the light energy. Photodiodes are exactly opposite to this. In photodiodes, when light falls on the diode, it generates electrons and holes. That is, the incident light is converted into electrical energy.
Hey, it's time to concentrate now.
Let's study construction and working of a photodiode. It is a diode which is always operated in a reverse bias mode. Due to reverse bias, it has a very wide depletion region. While using the photodiode, light is made to incident on the junction. The photons incident on the junction generate electron-hole pairs as shown in the diagram. Being in the reverse bias mode, holes get attracted towards the P region by negative terminal of the battery, and electrons get attracted towards the N region by positive terminal of the battery. We know that in a reverse bias mode, reverse saturation current flows through a diode. Thus, increase in the charge carriers leads to increase in the reverse saturation current. This current is called as a photocurrent. With increase in the light intensity, more electron-hole pairs are generated and the photocurrent increases. Thus, photocurrent is proportional to light intensity. What do we mean by dark current? It is the current flowing through a photodiode in the absence of light. Dark current flows due to the thermally generated minority carriers and hence increases with the increase in temperature. Think over, why are we operating a diode in reverse bias? During reverse bias, only reverse saturation current flows through the diode, which is in microampere range. The photocurrent that gets generated is also in microampere range. Thus, we can easily identify change in the diode current after generation of a photocurrent. On the other hand, if we operate the diode in the forward bias, then the diode current is in the range of milliamperes. Thus, a photocurrent of few microamperes won't create any effect on the diode current. Thus, we operate a photodiode in a reverse bias mode always. Let's see the advantages and disadvantages of photodiodes. Advantages of photodiodes are high sensitivity and high speed of operation. Disadvantages of photodiodes are poor temperature sensitivity. Dark current increases with increase in temperature. External biasing is required. Amplification is required as output is small. Now let us see the difference between a LED and a photodiode. LED is a light emitting device, whereas photodiode is a light detecting device. LED is always operated in a forward bias mode, whereas photodiode is always operated in a reverse bias mode. In LEDs, emission of light is a result of electron-hole recombination, whereas in a photodiode, photon generates electron-hole pair. Materials used for constructing LEDs are gallium arsenide and gallium phosphate, etc., whereas photodiodes are made up of silicon. Let's take a quick review of what we have learned in this lecture. Light emitting diodes, abbreviated as LEDs, are derived from a PN junction diode. When forward biased, they emit light in all directions. LEDs are constructed by developing 3 layers of semiconductor over substrate as N region, active region and P region. As electron-hole recombination occurs in active region, it emits light in all directions. LEDs are available in different colors as red, green, yellow, orange, blue, etc. They are widely used in street signals, displays of electronic devices like audio players, microwaves, etc. in the form of 7-segment displays. Next, we learned about photodiodes. When light incidents on a photodiode, it generates electron-hole pair and results in a flow of photocurrent. Photodiode is always operated in a reverse bias mode. We also studied what dark current is. It is the current flowing through a photodiode in the absence of light. Common applications of photodiodes are smoke detectors, compact disc players, in remotes of TV and air conditioners, etc.